Hi, so in this video, I'll be showing how to solve this mechanics problem which was asked in JEE 1995. So you can see on the top side, I have included the original question paper, and the purpose is just to show the diagram, this diagram, and the bottom you can see the question in English, and the diagram is slightly modified, so you can see in the above picture what was the original diagram shown in the question. So let's read the question, what it says. So a rectangular rigid fixed block, uh, uh, so basically this is the fixed block, and then there is a cylinder is placed along the edge, and what it says that the axis of the cylinder and the edge of the block are in the same vertical plane. So basically, if you see here, this is the uh, axis of the cylinder, and this is the edge of the block, and they are on the same vertical plane. And then they say there is sufficient friction present at the edge of this block so that a small displacement causes the cylinder to roll off the edge without slipping. So what is done is you give a small push to the cylinder, and then it will basically roll off the edge without slipping, and at some point it will lose contact with this edge, with the edge. And the first part says that we have to find the angle theta c through which the cylinder rotates before it leaves contact with the edge. So let's try doing this part. So so what we can do first, let's draw the this picture from as seen from the side view. So let me go to this page. So this is the rigid block, and then uh, okay. So this is what what looks like initially. Okay, and then yeah, there's a radius r. Yeah, so basically the axis of the cylinder and the edge of the stable, they are the same vertical plane here. Okay, so we have to find the angle through which the cylinder rotates. I'm just trying to see. The angle is with respect to. Okay, so the angle is basically from the time t equal to 0. So okay, so let's make another picture. And show the position of the cylinder at time t later when it is about to lose the contact with the edge. So basically this is the edge, not this is block, and this is the edge we are seeing from the side. So it just shows like a point here, but this is basically the edge of the block. Okay, so let's try to okay, so yeah, so this shows the position of the cylinder at time t later. So let's say this is the center, or basically the point through which the axis of the cylinder goes, and this is the angle theta c. That's what they're asking us to find. And so let's show some of the forces acting on this system, or basically on the cylinder. So there's gravitational force mg. Then there is a contact force applied by this block on the cylinder, and it is normal to the surface of contact. So basically it will be in this direction, this contact force. And the another force will be static friction, and the static friction will be acting in this direction. Okay, so yeah, so I think these are the forces. And what is the purpose of static friction? So static friction ensures that the cylinder is rolling without any slipping. Basically, this static friction will also provide a torque to the cylinder, and it will help cylinder to gain the angular velocity as it rotates along this edge of this block. Okay, so yeah, so basically let's solve the equations in this configuration. Okay, so the first is so yeah, so let me just and the radius of the cylinder is capital R. So this is also R. Okay, yeah, so and then this is theta. So and because the cylinder is rotating, the center of mass of the cylinder is rotating uh, uh, around the edge of this block, so there has to be centripetal force, and that will be provided basically by mg and normal force. So let's find the component of these forces along the radial direction. So this mg cos theta towards the center. So we have mg cos theta and then minus normal force, and this net force has to provide the centripetal force. And let's assume the velocity of center of mass at the point shown here is v, and the angular velocity is omega. So this has to be mv square over r. Note that this is centripetal force, it's not an external force. Rather, all the forces combined together should provide this force to make sure the object is rotating in a circle. Okay, so this is one equation, and because it is asking us to find the angle when it leaves contact with the edge, so the moment the cylinder leaves the contact with the edge, the contact force will go to zero, because when two things are in contact, there is always a positive contact force. So what we'll do is just set this to 0, and then what we'll get is v square is gr cos theta c basically. Okay, so we have two variables here, velocity of the center of mass and the angle. So we need another equation, and we can see if we can apply energy of conservation here. So I'll write a generic equation for the work energy theorem, which says that basically the gravitational potential energy for point 2. So let's say this is point 2 and the original was point 1. So gravitational potential energy plus kinetic energy at point 2 is equal to gravitational potential energy at point 1 plus initial kinetic energy plus the work done by all the forces other than the conservative forces. So the conservative force is gravitational force of gravity, so we won't include that, but then we have to find out the work done by all other forces. So you can see that the other two forces are contact force. The work done by contact force will be 0, because contact force always acts perpendicular to the uh, uh, basically perpendicular to the instantaneous direction of motion. So if you do a f dot d, it's always 0. So it's basically always acting 90 degree to the direction of movement. So this work done by contact force is 0. Now let's see what work is done by the Fs, the static friction. So here the cylinder is rolling without slipping. So let's see. Yeah, it says without slipping. So what does that mean? It means that there is no skidding or slipping. So the instantaneous so basically no skidding or slipping means at the point of contact. So it means the instantaneous velocity of the point of contact of the cylinder with the edge is 0. So which also means that V is basically V is equal to omega r, because V is the velocity of center of mass, and so the point of contact is here, and it is going back with omega r velocity. Because of rotation, it is going forward with the velocity v. So both have so net velocity should be 0. So which means v is omega r. And force of static static friction, work done by static friction is 0 in the case of pure rolling. And there are two ways to see this. One is one ways to look at that is to say that the basically uh, at the point of contact there's no movement. The point of contact is at basically at rest, because there is no slipping or skidding. So because the point is at rest, work done by the static friction is 0. uh, Basically it's the net work done by the static friction is 0. But in reality the static friction is doing actually work, but it's doing positive work and a negative work. So negative work, the way is the work is done, because so you can think like there's it is acting in opposite direction to the translation velocity of center of mass. So it is doing a negative work, which is equal to Fs times the distance delta x. Let's say center of mass moves by delta x. So the work done by static friction is minus Fs times delta x. But Fs also does a positive work in the sense that it applies a torque, and that increases angular velocity, and that work is positive and is given by torque times the, the angle the object rotates, the cylinder rotates, torque times delta theta. And if you see that the torque applied is basically Fs time r, uh, delta theta is actually delta x over r. So essentially you can see that this is also equal to Fs times delta x. So the net work done by static friction is actually 0. So yeah, we see that the W is 0 here. So it means we can use energy of conservation. Uh, we have what it means is when going from point 1 to point 2, the cylinder loses potential energy, and that has to be equal to the kinetic energy gained. So we can just say that delta U is same as delta K, and the change in potential energy is nothing but mg times change in the height. So you have to use simple geometry to find out this distance. So this is r and this is r. This much is r cos theta. So the change in height is r minus r cos theta. So r minus 1 minus cos theta c. So you substitute here, and then change in kinetic energy, basically the initial kinetic energy was 0, and at the point shown at the time t where the object has moved by theta c, it has two kinetic energy. One is rotational and one is translational. I mean, you can also do it considering it is a pure rotational around the edge, but I'll use two components. One is rotational, and so rotational is around its own axis, around the axis of cylinder, and translation is translation of the center of mass of the cylinder. Okay, so this is easy. So rotational is half I omega square, and then translation is half mv square. And then if we substitute moment of inertia of a cylinder is half mr square omega square half mv square. And we use the fact that v equal to omega r because it's a case of pure rolling. Then we'll get half 1 over 4 mv square plus this term, and then we'll get 3 over 4 mv square, and that has to be equal to mgr, 1 minus cos theta. So 3 over 4 v square is equal to gr 1 minus cos theta c. So we got the second equation, and the first equation was here. So we can substitute gr cos theta for v square. This, and then if you simplify this, basically you'll get 3 over 4 cos 1 minus cos. Alright, so cos theta c is 4 over 7. Yeah, so the answer for part A is cos inverse 4 over 7. Okay, so let's go to part B, the speed of center of mass of the cylinder before leaving contact with the edge. So it's asking the velocity v at this same time point. So that's straightforward. We can use the one of the two equations. So v square is equal to gr cos theta c. So it's 4gr over 7. So yeah, v is 4gr over 7. So this is straightforward. Now the last part, let's see. So the ratio of translation to rotation kinetic energy of the cylinder when its center of mass is in horizontal line with the edge. Okay, so what it is asking is, let me copy this picture. Okay, so it's asking when the center of mass is in horizontal line with the edge, we have to find the ratio of translation to rotational kinetic energy. Okay. So you can see that the cylinder has rotated about by 90 degree in this configuration, and it has already lost contact with the edge. So what happens is after losing contact with the edge, um, there's no static friction acting on the cylinder. So there's no, and of course there's no contact force. The only force now is mg, and mg passes to the center of the cylinder. So mg will increase the velocity of its center of mass as the object rotates after losing contact with the edge. But there's no net torque on the cylinder. So what it means is its angular velocity will remain same as what it was when it lost touch with the this block. So the omega will never change after that point. So omega, you have to use part B. So omega is basically V over R. and V we found in part B. So it's basically 4G over 7R. Uh, but and yeah, so this is omega, and it will always remain same. Yeah, so to find the velocity at this point when the cylinder rotates by 90 degree, we have to use conservation of energy. So so let's call it this as point 3, and uh, and yeah, either we can apply energy conservation with respect to point 1 or with point 2. So we can use point 1, that's fine. So basically point 1, so point 1 to point 3, the change in potential energy is mgr because the height is r, and the total kinetic energy is sum of uh, rotational and translational kinetic energy. So translation, so we have to find here the translational kinetic energy. Okay, so that is mgr minus rotational kinetic energy, which is half I omega square, and the omega has to be this because we said omega is not going to change. So mgr minus half I, let's say mr square, and for omega square I'll write 4g over 7r. Okay, so basically all this is actually only one r will cancel, so this term is mgr over 7. So you'll get 6 mgr over 7. This is the translation kinetic energy, and what they're asking is the translation rotation. Okay, so that's easy. Translation to rotation. Now this we found is 6 mgr over 7, and the rotational kinetic energy is this mgr over 7. So we get basically 6 is to 1 or 6. So yeah, I think we covered all the 3 parts. Uh, yeah, main thing I wanted to emphasize is the static friction does not do any work in case of pure rolling. Because it's pure rolling, the point of contact is at instantaneous rest, and that's why the force of friction is static. Otherwise, it would have been kinetic. So that's one thing, and then you use energy of conservation. And again, wanted to say that this centripetal force is not an external force or not an internal force. It's just the force um, uh, which is needed to be applied on object to make sure it rotates in a circle. And here there's a component of mg in the contact force. The net effect provides the necessary centripetal force.